Okay, for first step, we need to measure the initial diameter of the tension test sample into perpendicular direction using vernier caliper. You need to measure it twice, so you need to get the average initial diameter. Step 2. Measure the length of the specimen between the grips using a scale as it shows in the video and records the result. Next, punch marks are made at a distance of 2.5 diameter. 2.5 diameter means 2.5 times 12.82 and you will get 32.05 millimeter. So, distance between each punch marks is 32.05 millimeter. Step 4. Insert the specimen into its position and mount extensometer on the specimen like it's shown in the video. Step 5. We need to make sure readings on the dials A and B of extensometer are adjusted to 0. For step 6, experiment is conducted. Turn on the button and load extensometer readings are read at regular intervals of load up to the yield point. Ivory scale readings are noted to the specimen failure. This is the graph from the data that we get. The graph is load versus ivory scale reading. Second graph is load versus extensometer reading. The graph look like this. Step 9. Join two pieces of the test sample and measure the diameter at the neck of the specimen. Last step is measure the final length between three punch marks like it's shown in the video. To calculate yield stress, formula for yield stress is load at yield point over A node. As we can see, load at yield point is 43. So, 43 times 10 cube over 129.02. Why 43 times with 10 cube? Is it because 43 is in kilonewton? So we need to change it to newton. So we need to times it with 10 cube. So when you calculate, we will get 333.28 Newton millimeter square. Next, to calculate tensile strength, formula for tensile strength, ultimate load over A node. Ultimate load, as you can see, 49. Ultimate load is the highest load that we got from the experiment. So, for this experiment, we got 49. So, 49 times with 10 cube over 129.02 and we'll get 379.79 Newton millimeter square. Next, to find modulus of elasticity, the formula is slope times 1 over LC times gauge length over A node. To find the value of slope, we can get it from the graph, which is like in the picture, which is slope is 2.27, or you can calculate it. We need to find the point X and point Y and find the gradient. LC is least count, which is 0.01, so replace it in the formula. You will get 2.27 times 1 over 0.01 times 120 over 129.02. Calculate it and you will get 2.244.06 GPa. Next, calculate the percentage of elongation. How to calculate the percentage of elongation? The formula is initial diameter minus final diameter over initial diameter times 100. initial diameter, which is we can get from the result 12.82 minus with final diameter, which is 7.86 over 12.82 times 100, and you will get 38.69%. For percentage reduction in area, we use the same formula as percentage elongation but change it to area. So original area minus final area over original area times 100. Original area, which is 129.02 minus with 48.5 over 129.02 times 100, and you will get 62.41%.
Discussion of tensile test. As we know, strain refer to the results of stress-strain diagram. As we know, the first region is elastic region, where the material will return to its original shape after the material is unloaded. The stress is linearly proportional to the stress in this region. Yield strength, where a point at which permanent deformation occurs. Next, we have plastic region. If the material is loaded beyond the yield strength, the material will not return to its original shape after unloading. It will have some permanent deformation. If the material is unloaded, there will be a curve. Next, we have ultimate tensile strength UTS or tensile strength TS, which is the largest value of stress on the diagram. It is the maximum stress which the material can support without breaking. After UTS, there is strain hardening. If the material is loaded again, the curve will follow back with the same elastic modulus, which is slope. The material now has a higher yield strength. Raising of yield strength by permanently straining the material is called strain hardening. Lastly, we have fracture. If the material is stretched, the stress decreases as necking and non-uniform deformation occur. Preparation for tensile test. First, setting the testing parameters. Once the machine has been calibrated, the testing parameters should be set. This includes the speed at which the test will be conducted, the maximum load that the machine will apply, and the data acquisition rate. Second is conducting the test. With the machine calibrated and the parameters set, the tensile strength test can begin. The machine will apply a load to the specimen and the deformation will be recorded in real time. The test should be conducted at steady pace and any deviation from the testing parameters should be noted. Next is analysis of the results. After the test is complete, the result should be analyzed to determine the tensile strength of the material. The tensile strength is calculated by dividing the maximum load applied by the cross-sectional area of the specimen. Any anomalies or variation in the result should be investigated and noted. This is because error might occur and, for example, typing error and so on. Lastly, reporting of the results. The result of the test should be reported in a clear and concise manner. The report should include details of testing parameters, the result obtained, and any observation or conclusion that can be drawn from the results.